To start, we could both come up here and you could turn everything back on that we need to. I don't want to mess anything up by accident.
Turn everything back on as in this stuff?
I mean, it's just click on the. I guess it's just start here, isn't it?
Yeah.
Okay, so we should be good.
Yeah. So you'd have to click on the three eye icons, that's all.
Okay, easy enough.
And then
And you can have it pulled up on
there'll be a
laptop
delay
too. Make
though.
sure it all sounds good.
Yeah.
Yeah. But if there is like an issue, just like stop me
Gotcha.
right when we get started. I guess.
We'll do.
Right.
I'm gonna leave it on this window for now, just so we can toggle this. But the broadcast should see only the image.
Yeah, we'll have to change it here too. So it's just swipe up. Okay. Easy enough.
Yep.
Awesome.
I was saying we need to talk to you more about your structure. We have it. We've been talking. Yeah.
I was going to come that way today.
I was saying we should go talk to us.
It's like a power thing.
No, I wasn't gonna like.
I also
I have to look at it. I think it's done now, right? Wait, he's in 10th place? No, he's in 10th place. Right there. He's on the screen. Oh, Scott's here.
I don't think you guys already started.
So Corey is now, I should tell you about the typo on your slide. Both of them? Fine. Oh, what's the typo? Well, you're about to find out.
Okay, how do you turn this one on?
Just push.
Okay, there we go. All right, thank you everyone for coming. We're gonna go ahead and get started. Thanks for waiting the extra couple minutes just while we set everything up and waited for everyone to kind of wander on in. So welcome to the Spaceport America Cup Critical Design Review. For those of you that don't know me, my name is Sarah Malaska and I'm the project manager this year. And make sure you guys, as you walk in, you grab attendance in the back as well as the review forms. So the purpose of the Spaceport team, as most of you know, is to compete in the Spaceport America Cup. This year, that'd be the 2024 Cup, and this is hosted by the Experimental Sounding Rocketry Association, better known by Ezra, on June 17th through 24th of this year. We also develop and present Asteria, our rocket this year, which is BSLI's most refined and technically advanced high-power rocket. And then finally, our last purpose is to meet and engage with other members of the intercollegiate rocketry community, which we primarily do through our competition. All right, as for our goals and values, we of course want to have a nominal flight in our category, which is 30K SRAD, or Student Research and Design. We also need to conform to Ezra's rules on design. Something our team really likes to do is to focus on a majority SRAD final design, so we try to make as many of our own rocket components as we can. We also like to supplement academics with hands-on engineering experience, since we all know we don't get the most hands-on experience in our engineering classes. And then finally, another goal of ours is to maintain a thriving rocketry community at Ohio State. All right, as for our trajectory, last year we placed 82nd overall out of 119 teams at the 2023 Cup, and we placed 4th out of 5 total teams in our category. As most of us know, this was because of a structural failure that occurred close to 10,000 feet last year. So this year we're aiming to understand that problem as well as the issues that we encountered at the 2022 Cup. In 2022, we had a lower apogee than expected due to a motor malfunction. To do so, this year we're placing a greater focus on analysis, simulation, and testing of the rocket and its components. So you'll hear more about that from each of the sub-team leads as they run through their individual systems and slides. We also aim to advance the abilities of our current sub-teams. And this year, something new that we're doing is including air brakes so that we can closer reach our target apogee and improve our final score. A big part of the Spaceport America Cup is getting as close as possible to that 30,000 foot goal. And then finally, right now we're currently preparing for our first test launch on March 30th. Before then, we're hoping to do a test integration in the next couple of weeks as we get into early March. I'll now hand it off to Ram, our deputy project manager, and he'll lead you guys through our team breakdown and a couple other introductory slides.
All right, hi everyone. I'm Ram Sai Ganesh, the Deputy Project Manager for the Spaceport team. Here's an overview of our leadership. Our team is led by Sarah Malaska, who we met before. I'm Ram Sai Ganesh, the Deputy Project Manager and the team's Safety Officer. Our Structures sub-team is led by Corey Mays. Our Payload sub-team is led by Corey Ireland. Avionics is led by Peter Hall. Recovery is led by Calvin Beal. Propulsion is led by Advait Saraf. Aerodynamics is led by Sawyer Haman. Here's a quick overview of the rocket itself. Our predicted apogee with our air brakes is right around 30,000 feet with, we expect some variance around there because of environmental conditions. Without the use of air brakes, our rocket would reach around 34,000 feet. we reach a max velocity of 2,315 feet per second, which is Mach 2.05. Our maximum acceleration will be 17.78 Gs. The mass of the rocket with the motor is 81.695 pounds at liftoff. As for an overview of the CDR itself, the sub-team leads will present in the order in which they were introduced. We'll start with structures and then move on to payload, avionics, recovery, propulsion, and aerodynamics in that order. Each sub-team will present their purpose, the requirements of their subsystem, an overview, followed by a breakdown, and then any testing and validation methods, and then any risks they foresee encountering and their mitigation strategies for those risks, and then move on to their schedule for the entire year, and then have 5 minutes at the end of each of their presentations for questions. If you haven't already, please pick up a review item disposition on the table near that entrance. All right, over to Corey Mays, our structures lead.
Thank you, Ram. That was awesome. I'm Corey Mays. I'm the structures lead. Our sub-team purpose is to construct the airframe of the rocket, allow for integration of other sub-teams into the rocket, design and manufacture the air brake system, validate design decisions with computational analysis and material testing. The requirements, the parts must withstand loads from supersonic flight to 30,000 feet, efficient integration of the entire rocket, smooth finish to the airframe parts to reduce adverse aerodynamic effects, and design air brakes that produce enough drag, withstand drag loads, and have consistent deployment metrics. System overview. Some of the parts that we make, or all the parts we make, are the nose cone, body tube, recovery bulkhead, the payload systems bay, the air brakes, the coupler, and the transition piece. And to kind of briefly go over integration, because Peter wanted me to. The little blue box right below the air brakes, that's the avionics bay. They'll slide into the coupler, be totally encased in the coupler. The air brakes themselves also slot into the top of the coupler. Payload bay above that and recovery bulkhead. All these are being connected and secured by threaded rods that run up the entire body tube. The body tube and nose cone are made from carbon fiber. Payload bay has rails that are made from carbon fiber and bulkheads that are made from carbon fiber honeycomb sandwiches. I'll go over that more later. Same with recovery bulkhead is the honeycomb sandwich. The transition piece is a fiberglass piece, and I'll go over more of that later. But, first, looking at the parts we make, the test motor tube. So our test motor is slightly smaller than our competition motor, so we use a 75 millimeter motor for test launch. So we need to make a motor tube that adapts from the 75 millimeter to the 4-inch motor tube of our coupler. The tubes are made from carbon fiber. The outer tube is 6 layers aft and 14 layers forward. The reason for this is because the mandrel that we have that's closest to size is when we were using 98 millimeter motors. So to have the forward side of this tube fit into our competition size coupler, we added extra layers of carbon fiber to get that up to size. Yeah, so with all this extra material, we suspect that just caused more air gaps or imperfections. So there were some gaps in the roll, but we filled those with Bondo, structural body filler. Some of the parts that are made from carbon fiber wood core are the centering rings, which are machined identical, turn on a lathe. That way your thrust is completely axial to your motor tube, and you don't have bad moments acting on your coupler. The fins, which are also the wood core, and we 3D printed.
Looks like the stream's still going.
Is the stream still going?
Yeah, stream's out.
Okay. All right, I don't know where I left off on the stream, but I'll just keep going. The epoxy, high strength, high temperature, so it should be able to withstand the loads from the motor as well as the heat from the motor. Transition piece. So this transitions our airframe from the 6-inch body tube to the 4-inch motor. It's an aerodynamic part made from 4 layers of fiberglass. The reason it's fiberglass is because carbon fiber would attenuate radio frequencies, and the transition is where our avionics bays antennas will be. So we need to have the radio frequencies be able to transmit to our ground station. Since our geometry of the 6-inch to the 4-inch motor's not changing, the geometry of the transition doesn't need to change. So we're using the same mold as last year, so a 20-inch long transition piece. The coupler, this is our load-bearing part that connects the motor to the body tube. Same design as last year, so a lot of the analysis and testing that was done on it last year still holds. But it's made from aluminum, 2 tubes, 6-inch OD to the 4-inch IED, welded together on a plate, and then we put it into a lathe to ensure concentricity. Slightly different manufacturing process, however, instead of using the coupler mandrel to turn it, we used oversized tubes in thickness and length to make sure that this part is concentric. A body tube. It's carbon fiber. It's the airframe part that contains all avionics, payload, and recovery bays. Carbon fibers, this is a structural piece. So we went 6 layers of carbon fiber based off of last year's material testing and progress there. And different this year, however, is we need to manufacture or cut in slots for the air brakes to stick out, which we do expect, obviously if you're cutting into carbon fiber, it's going to weaken it slightly, but I'll go over later how we're going to strengthen that. Nose cone, obviously the point of failure last year. However, this year we've remade everything, remade the plug, which is this top left photo, is this MDF plug, the basis for our mold. So this plug is 1-to-1 what our nose cone should be. So yeah, we remade that. It is the correct dimensions now. We laid up our mold on that, 2 halves of the mold. You can see on the top right picture is a mold layup. And then we stick those 2 halves together and lay up the nose cone inside the mold. You can see in the bottom left is a picture from the layup that we did. This is, again, mostly an aerodynamic part. Some structural loads, but not as much as other structural pieces would experience. 4 layers of carbon fiber, same shape as last year, Von Karman, the same length, 28 inches. Slightly different this year is the 9-inch coupler. This will help with fluttering issue, but is also a new spaceport regulation that the coupler length needs to be 1.5 body tube lengths, or body tube diameters. And then the orange nose cone. So I attribute this obviously to the bad mold release. So when we lay up the mold, we use an orange gel tooling coat to get a clean finish and get into like the nooks of the plug. And so when we lay up the nose cone, we spray, used to be free coat, but some sort of mold release. Free coat got discontinued, so we've been using kind of knockoff stuff from Lowe's and stuff, and I think that mold release is just not up to par with what we're used to. So when we took the nose cone out, it ripped up a lot of the orange gel tool coat with it. Not an issue because we can just sand it. Well, it wouldn't be an issue unless we had to remake the nose cone, which I don't expect we will. Because we'd have to remake the molds, but not an issue now because we can just sand this orange gel coat off pretty easily. Recovery bulkhead. This design is more representative. Calvin will go over in depth what the recovery bulkhead layout will actually look like, but as for the structure side, this is where the recovery bulkhead, or the recovery hardware will be housed, and the avionics connections will be integrated to for the avionics recovery connections there. The bulkhead itself is made from the carbon fiber honeycomb core, which I was talking about earlier, and then we'll have a carbon fiber L bracket that compresses an O-ring to seal this way that, for 2 reasons actually. So recovery can build pressure in their bay to blow the nose cone off, and also so any products from that, the energetics, don't blow back into the other bays and ruin things there. Payload systems bay, this is where the payload will go. The bottom bulkhead is another one of those honeycomb sandwiches. The top bulkhead, outdated in this picture, but it will be aluminum because avionics will have a secondary bay up there, and they'll talk more about that later, why they need a second bay. But they need to mount hardware and other stuff on it, so they requested an aluminum bulkhead, so that's what it will be. And these rails, like I said earlier, are carbon fiber. Air brakes. So this is our design for the mechanical system to deploy the drag-inducing blades. This is entirely made out of machined aluminum, CNC'd. The housing plates, those were done through Protospace, Spaceport sponsor. And the motor horn linkages and blades, those were done here in Scott with my friend Kevin. But we're very proud of these. I think they came out really well. The tolerances are tight and they fit very well together. And you can see here on this top plate, in the bottom left picture, it kind of, the top plate kind of raises it up into a tube section. This is where we'll plan to remount the body tube to add additional structural support around the area where we're having cutouts for these blades to stick out. Testing and validation on the right, there are pictures of things we've already done, such as the FEA on the body tube, like I just mentioned. You can see that the slots on the bottom there weaken areas around that section, so remounting the body tube onto the air brake tube will definitely help strengthen it there. The air brake blades, we did projected loads from aerodynamics onto the air brake blades. This helped us determine that we can reduce the width of the air brake blades, and also gives us metrics on the motor torque specs. And then recovery bulkhead on the top there. It's hard to do FEM, an accurate FEM simulation on composites, and especially honeycomb, and especially when you sandwich them together. But this gives a good view of like layout and where stresses would be concentrated, so we can plan better for the recovery bay layout. But as for other testing and validation we're doing, recovery bulkhead testing, like physical testing, load test, and ejection test. So we're going to put actual expected loads on the recovery bulkhead to make sure that this design will work when we do test launch. Air brakes testing, fit test we already did. You can see in the last slide, the air brakes were assembled. Friction test, we're just going to slide the air brakes around how they would be in flight and make sure that there's nothing stopping it, or get the right amount of lubricant needed in the air brakes. And then a load test. This is to test the motor specs to see if we can deploy the air brakes with the projected loads of flight applied on them. Integration test, so practice and optimize integration procedure. Obviously, so make sure everything fits together well and goes smoothly on launch day. And test launch is the proof of our structural components, and we use that to analyze any structural failures. Risks to project success, time shortages, fabrication errors such as poor layups, out of tolerance parts, breaks, cracks, integration failures, so poor processes leading to broken parts, test launch failures, crash landing, structural failures, anything that would constitute a refabrication. Risk matrix. So for time shortages, the impact would be minor and the likelihood is possible because we're getting down to the crunch time of the year, and is at our current state, we do have a lot more work to get done, so definitely possible. Impact would be minor just because it just mean coming in more after hours, not on meeting times, just working on it. But the way to mitigate that is to, during meetings, to stick to the timeline and ensure process efficiencies. Fabrication errors, the impact would be minor and the likelihood is unlikely. At this point of year, we've been making the same parts for quite a while now, so we're pretty good at what we do, I guess. But to mitigate that would be detail-oriented mindset when we're laying up, and ensure that the team is prepped for layups. Integration failures, likelihood is unlikely. Again, if we can get all our parts up to spec before integration, then when we're integrating, it should go fairly well. But the impact could be significant. If we break apart on integration, then that could either delay our launch or completely cancel the launch. So the way we mitigate that is well-documented procedures and label orientation lines, and practice integration, obviously. Test launch failures, likelihood possible, given certain track records of the team, but the impact, of course, is major. And the way we mitigate that now is all the tests we're doing, the computational analysis that we're doing, and the validation of the structural parts, so that when test launch comes, we're confident that these our parts will be able to withstand the launch. Our schedule, so throughout the year and currently and in the future, we are testing and validating these parts. Last semester is when we laid up all our bulkheads, made the PSB. We started the motor tube, we finished it at the beginning of the semester. The body tube, we just laid up a week ago, less than a week ago, I think, actually. But beginning of the semester is when we were starting the nose cone mold, laid up the transition, and then we also just laid up the nose cone pretty recently as well. So now we're looking at finalizing all these parts and getting them ready for test launch, and then competition launch. And then the air brakes, the design of the air brakes was last semester, even before last semester, started during the summer really, but manufactured quite recently, beginning of the semester. So now any questions?
If we don't have any questions in the audience, we'll wait a couple seconds just to see if any questions appear in the chat, since they're a little bit of a delay for the live stream. Something that we did get asked that we also answered in chat was from Jonathan Winkler, and he asked if the issue last year is tied to a fabrication error. We answered in the chat that it was due to an outer dimension nose cone,
Right.
but feel free to elaborate on that too.
Yeah, it wasn't a fabrication error. So even after the launch, when we recovered the nose cone, surprisingly, the nose cone is survived very well throughout that endeavor. But no, it was an out of spec part. The nose cone was undersized, which created a big gap between the nose cone coupler and the body tube. And the leading theory, most likely theory, is that the nose cone aerodynamically fluttered and pretty much broke out of the body tube. So not a true structural failure per se, but I guess it would fall on the structures team. But yeah. Oh yeah.
So a couple things about analysis. You're reusing your transition piece design.
Yeah.
Which you had last year. So what analysis shows it was the right design last year? We're redoing it, but you didn't show me anything to say it was a good shape last year, just that you're redoing
Right.
it.
Yeah. So that's probably an aerodynamics thing, really. So I think Sawyer will elaborate on the transition design and why 20 inches or slanted shape will be the optimum for this. But I know it's the geometry of going from 6-inch to a 4-inch, right? Something like that. But yeah, Sawyer can elaborate more on that during his presentation.
Tying into that, then right after that, you talked about materials selections, and based on last year's testing, we used blah blah blah. Well, as an audience member, I have never seen last year's
Right.
material testing. So, what did you test? What did it show? What?
Right. Yeah. So a lot of the tensile testing was making test strips of composites, varying layers and carbon fiber types, and they put that in a tensile tester to pretty much get the data to determine what optimal amount of layers would be good for the body tube per se. So I think I mentioned that on the body tube part, right? Yeah.
And then since I'm on the analysis train, one last thing at the end, you were talking, I think it was your air brakes on slide 20. Did we look at any like frequency analysis, vibrational analysis of what they might, because straight loads is one thing.
Right.
But the shaking.
Right, yeah, I definitely think that's not something we have looked into at this point, but I definitely think it's worth looking into, especially since they're not a tight fit, and then nothing ever will be. And but with the shaking issue with the nose cone, I think it's definitely worth looking into with other things that will be deployed into the flow, like the air brakes. So I definitely think that's worth looking into.
There's no more questions in the chat.
So, anything else from audience? All right, thank you guys.
Great. Next up is Corey Ireland to talk about payload.
All right, hello everybody. As Ram said, I'm Corey Ireland, and I'm this year's Spaceport Payload Lead. I'll start off by kind of going through what are our goals for this year. At the very most basic level, we have to design and manufacture a payload bay conforming to a 5U CubeSat structure. Now, for those of you who aren't familiar with what a U is, in the satellite industry, it's basically a 10 by 10 by 10 centimeter cube. So a 5U payload is 10 by 10 by 50 centimeters. We also are looking to incorporate an outreach payload, which I'll discuss later, into the bottom 1U section of our payload. And our main technical engineering goal is to rotate a stabilization capsule to maintain its orientation relative to the rocket's acceleration vector. We are also looking to reduce vibrational loading on that stabilization capsule through a polymer structure we've designed. More on the scientific end, we are hoping to determine the payload's ability using that stabilization capsule and vibrational absorption system to protect a benign strain of E. coli from aeration in flight. And lastly, we are hoping to win the payload award at the Spaceport competition in New Mexico this summer. Some of the system requirements we have are dictated by the ESRA competition judges, and some are self-imposed. The payload has to be completely self-contained, so no wires or anything going from payload to the other parts of the rocket. That is an ESRA requirement. We also cannot alter the rocket's flight path, so if the payload is replaced with ballast of the exact same weight and form factor, the rocket would fly the exact same. We also have to fit within, like I mentioned before, that 5U form factor. That's not necessarily a hard requirement by the ESRA judges, but it does get us bonus points in the overall competition. Also, we have to be between 3.81 kilograms and 4.08 kilograms. That minimum is set by the spaceport judges, so we can't fly a super small rocket. And the upper cap was dictated by our project manager when accounting for the motor we want to use. We also do not want to lose containment on our biological E. coli, not because it's dangerous or anything, but because it would invalidate all the data we collect on that. So here's kind of here's an overview of our overall payload. The frame is kind of that steel gray structure you can kind of see surrounding and encasing everything. I'll also talk about our mass tracking system to help remedy issues we've had with the payload being overweight or underweight once we reach competition. I'll also talk about our capsule rotation system, which takes that black sphere and rotates it around. That's what our scientific experiment is located within. I'll also talk about our vibration reduction system, which utilizes that honeycomb polymer that I'll talk about. We're also tracking the current rotational position of that capsule using computer vision. And then we also have those scientific experiments I mentioned. So there's that E. coli, and then our outreach experiment, which I'll elaborate on. And of course, all of this is run through electrical and software means. The electrical component is located near the top of the payload, and that also runs our software for controlling everything. First up is that overall structural frame I talked about. Like I said before, we have a 5U CubeSat form factor. Now, if you're a veteran of the Spaceport team, you'll note that payload has always been 3U. However, due to the space requirements of our complicated mechanical system combined with the need for a lot of electrical components, we had to bump that up to 5U. However, despite being a much larger in terms of volume, it's still going to be roughly in line weight-wise with payloads in prior years. We also redesigned our structure to better take advantage of our CubeSat structure. Traditionally in the past, the frame has been made by bracing rails using panels. This year, we're capping those rails, as you can kind of see in that design, in that CAD model below. This also allows us to build the payload as 3 separate kind of modules that we then screw together. This means that in order to modify one part of the payload, we don't have to take the entire thing apart. Also, in order to take advantage of our CubeSat volume, we also reduced our rail width. Traditionally, our rails have been 1 centimeter squares. This year, they're 6 millimeters. In order to justify this change and make sure it wouldn't impact the structural integrity of the rocket, very early in the year, we ran some ANSI simulations under our expected loading of the payload in order to make sure that these would survive the rigors of launch. Next, I'll talk about our mass tracking system. Historically, in the past, when we go to spaceport, our payload has either been overweight or underweight, and we've been taking pieces off at competition or screwing more metal pieces on in order to get us up to our required weight. This year, I want to make sure that wouldn't happen. So I've implemented a system for tracking the end goal mass of the payload, even very early in the design process. How it works briefly is like this. We have one spreadsheet that contains a list of all of our parts that are in the payload, including data such as their overall estimated mass and how far along they are in the design process. All those parts and their part numbers are then logged in what is essentially a mirror of the part tree that is in SolidWorks. This allows us to, this allows us to keep track of where parts are in the payload, and if a part's, let's say the mass of a part changes, all we have to do is change it in the part list spreadsheet, and that automatically propagates out every place that part is located in our overall part tree. And by logging that part tree every month, that generates our historical mass tracking graph, which allows us to see how the mass of the payload is evolving over the course of the year. On that graph, you can see the red and green lines are our bounds for how heavy the payload should be at the end of the year, and that blue line is our current best estimate for what that payload will weigh once we're finished with it. And based off the maturity, the design maturity of our various parts in payload, that's how that orange and light green lines are generated, which kind of show the bounds of how the payload mass could change as it goes on. So as the design matures, you can see those lines are all getting closer together, and by the time we reach competition, all 3 lines will converge between that red and green bounds. Next, I'll talk about our rotation system. This is the main mechanical component of our payload. Last semester, we were really focused on going through prototype iterations to really refine this system and make sure that it operates properly and smoothly. This picture up here is of our very first prototype we built, and I think that was back in October. This picture is our most recent prototype, which incorporates a lot of parts that will go into the final payload. Essentially, at a high level, the main component is that spherical capsule you can kind of see there in the middle. It's 3D printed in one piece out of PETG, and it is coated in a styrene butadiene copolymer coating. Back during our initial prototypes, we actually didn't have that coating, and it was our omnidirectional wheels were having a lot of slippage on the slippery plastic. So we coated it with what is essentially liquid rubber in order to increase our friction so that our wheels could properly turn the capsule without slip. Those omnidirectional wheels allow us to rotate the capsule in any direction, even against the even sideways along the wheel, because they have essentially a ton of small rollers on them that allow us to move sideways with little friction. A lot of our early prototypes had trouble with having enough torque to turn that capsule because of the spring loading. Because it's spring loaded, it requires a lot of torque to turn that capsule. And we actually ran some tests and found that it took 6.1 ounces of torque to turn the capsule. So we ended up, for our final design, we selected servos that output around 20.86 ounces of torque. Now the reason to have such a high safety factor there is because we can't do any kind of any testing under our expected G loading of launch. So we anticipate that the required torque to turn the capsule during launch will be higher than what it is on the ground, hence the high safety factor. And like I kind of just alluded to, this whole system is spring loaded in order to maintain pressure during launch, even as the rocket accelerates in different directions. Now I'll talk about our vibration absorption system. So as you can kind of see in the picture in the bottom left there of our CAD model, this is positioned between our stabilization rotation system and the electrical bay. And there's essentially a mirror of this on the other side. So the entire rotational system is compressed by 2 sets of these vibration absorption polymers. In order to do the analysis on such a weird material as thermoplastic polyurethane, which is what these are made of, we use a 3rd order Moonley-Rivlin analysis. This allows us to take into account the hyperelastic parameters of a material like TPU. Additionally, we didn't want the force of that compressive force I talked about to be going straight through the stabilizer, because that would mess with our spring loading that we already have on that whole rotation system. So instead, we have these polymer sandwiches pressing against the panel you can see pictured in the bottom right, and then that force then transmits through the rails that keep the stabilizer together. In order to save weight, we did a lot of ANSYS analysis on those panels to get them as thin as we could while still maintaining structural integrity. Eventually, we were to get them down to, I believe it's 1 millimeter was the final width of those panels. So in order to track the current position of the ball, we can't put a gyroscope or an accelerometer inside the capsule because we can't have a wire coming out and leading to the rest of the payload because it spins around in all different directions. That just wouldn't work and the wire would get tangled. So we're using a computer vision system with 4 cameras mounted in positions around the capsule. Early in the year, we built a custom a ray tracing library, which allowed us to essentially simulate positions for the cameras and allowed us to simulate all the different orientations the capsule could possibly be in order to determine and ensure that no matter what position the capsule is in, we will always be able to see one of our markers by one of the cameras. And speaking of those markers, originally we planned on using essentially colored dots in order to derive the position of the capsule. However, last semester late, we had the idea of using what are called Aruco markers, which are essentially QR codes that are tracked by the cameras. These are used a lot in industry when rollers are moving packages around and all of that, and we decided they would be perfect for our case. You kind of see some of our preliminary computer vision there in the bottom left. We place those markers evenly on the surface of the sphere using what's called a Fibonacci lattice, which is a method for placing points relatively evenly distributed on the surface of a sphere. Now I'll talk about the scientific goals of this payload. The primary goal is E. coli. We're looking at protecting E. coli from aeration. Now, if any of you aren't familiar with what aeration is, I know I wasn't before we started this. Aeration is when you have a biological material suspended in a fluid, and when you shake it around, it spreads oxygen throughout the mixture, which enables the bacteria to grow faster. So through this system, we're hoping to prevent that from happening. We're hoping to observe our samples post-launch. We'll have one sample that's located inside the capsule. You can kind of see that cavity there in the middle. That's where our sample will go. We're going to put it in those kind of COVID sample spit tubes. I don't know if you guys remember that from a few years ago, back when we had COVID testing. We're putting our samples in there, and that slides into the capsule. We'll have one sample in there, one sample in a different location outside the payload that's not protected by our vibration reduction system, and one sample on the ground as a control. So once we recover the rocket, we'll take those samples and put them next to each other and wait for them to grow. And hopefully, if our vibration reduction system is successful, the E. coli sample that was in the capsule will be less aerated and will grow slower than the other 2 samples. Now, early last semester, we went to a local high school in Columbus into the outreach program where we guided a class separated into groups through essentially the shortened version of the payload design process. And we're looking to implement 2 of their ideas on the payload this year. The first is a cologne observation experiment. We're looking to measure pH changes in the cologne over the course of the flight of the rocket. One of the reasons we picked this one is it's small and it fits with the E. coli experiment. One of the other groups in that class came up with the idea of mounting a magnetometer on the payload in order to measure the changes in the Earth's magnetic field with altitude as the rocket ascends. This was picked because it is small, simple, and we can fit it in with the rest of our electrical bay without too much difficulty. This is one of our more complicated payloads in spaceport history, at least in terms of the complexity of the electrical systems. We're using a Raspberry Pi microcontroller because it's very well documented, and our payload sub-team members already have experience with Python, which is what we're using to control everything. One of the other big components is our camera combiner, which allows us to use 4 cameras simultaneously, despite the Raspberry Pi only having 1 slot for a camera to plug in. We also have our servos that control the rotation of the capsule, along with our sensor suite. You can see the magnetometer I mentioned earlier. We're also using an environmental sensor to make sure that payload temperatures don't exceed the maximum bound temperatures of some of our parts. On the software side, the biggest challenge so far has been that takes in our camera data and camera footage in a matrix of RGB values, and then from that it derives the actual current position of the capsule, and then from our accelerometer that's located in the electrical bay, we get our target position. And based on the difference between those 2 positions, we feed that into a PID controller, which then outputs the desired rotation speed of the capsule. And that then gets fed into some linear algebra we're developing, which outputs the desired speeds of each individual servo rotation. In terms of testing and validation, one of the big tests we want to do in late March before the test launch is what I'm calling a dark test. Essentially, it involves us putting the payload in a dark container or a dark room and running our computer vision to make sure that the cameras can still see those little QR codes only through the light of the LEDs mounted on the payload. Of course, we have our 2 test launches later this semester. The first test launch, we're not going to have that 5th U that has the outreach experiments in it because that's simply not necessary, and we want to devote our time, all of our time right now towards making sure the rotation system works. So the main goal of that test launch will be testing the rotation under the loading of launch conditions. For the second test launch, we'll have our full payload with the 5th U to make sure that everything structurally is good and everything integrates properly. And the big goal there will be testing our refined rotation algorithms, learning what we used at the first test launch. After those test launches, we want to conduct what we're calling an oven test at our maximum expected temperature. We're anticipating running that in mid-April. We'll be using the data from our environmental sensor of the temperature of the inside of the rocket and extrapolating that difference out to what we expect the difference between ambient and internal temperature of the rocket will be at spaceport. So we can run our oven at whatever temperature we believe the inside of the rocket will be at competition. We're also hoping to conduct a shake test of the entire payload. This will involve us taking the full integrated payload to a shake table, which we are still working on trying to find, and putting it through a vibrational regimen in order to make sure it'll survive launch conditions. Lastly, we're hoping to conduct full ANSYS simulations of the entire payload structure in order to verify that it'll be able to survive all the way up to 20 Gs because the test launches are not quite as rigorous as our actual launch. In terms of risk to project success, obviously the big one is somewhere in the payload having a structural failure. Additionally, we could have the batteries lose charge because we're sitting out in the sun of New Mexico for a long, long time on the launch rail. We could also have the control systems failing in a high G environment because we can't really simulate something like that on the ground. Then lastly, we have our servo maximum temperatures being exceeded. Those maximum temperatures are about 140 degrees Fahrenheit. In terms of mitigating our risks, just for a bit of context on the impact part of that slide, since payload can almost never have an effect on the rest of the rocket, all those impacts are in the context of payload alone, not of overall mission success. But the first one, like I discussed before, is our payload structural failure. We're hoping to mitigate this by running ANSYS simulations, we have our test launches, and that shake test. In terms of the batteries losing charge, we're trying to mitigate this in 2 ways. First off, we have run power calculations on the power draw of our various electrical components and use those to calculate how much battery we should need, both sitting on the ground on the pad, as well as how much we're going to need in flight when we're actually running those servos and the hardcore electrical components. We're also working with the avionics sub-team to develop a remove before flight tag. That way, the payload doesn't have to be on during our integration and we're transporting it out to the pad. The payload will only turn on once you remove that tag, once the rocket is already on the rail. In terms of the control system failing, under high G loads, we have those test launches I mentioned. Those get us most of the way to our expected G loading at the actual launch. And then we have that extra servo torque margin that we built in when we selected the servos we're planning to use to rotate the capsule. For exceeding the maximum temperatures of our servos, we have those test launches, and from those test launches, we will collect data on the difference between ambient temperature outside and temperature inside the rocket. We can extrapolate that difference out to the expected ambient temperature at New Mexico to see what the expected temperature is inside the rocket at launch in New Mexico. And we will incorporate those temperatures, not only just are they below that 140 degrees Fahrenheit of the servos, but we'll incorporate those into our oven test to make sure there's no other unexpected wrinkles. In terms of our schedule, last semester, our primary goal was iterating through those various prototypes, moving closer and closer to a higher fidelity prototype of what actually goes onto the rocket. We also, towards the end of the semester, started working on those computer vision components, working on tracking those QR codes and checking where they are on the screen. Recently, we started working with our latest prototype on our basic controls, so moving the capsule in a coordinated manner using all 4 servos moving at once. And in the coming days, we're hoping to move into doing our integrated controls, combining the computer vision aspects with the mechanical aspects in order to essentially start building our final control algorithm. We also recently started our assembling our final metal bays. Those are made out of steel, and we spent a lot of time the last couple weeks in the mechanical and aerospace engineering machine shop, machining those and getting them ready for assembly in the coming weeks. Once we start executing our test launches, we'll also move into designing our outreach payload, which will then be integrated into that 5th U. And then lastly, from our test launches all the way moving out up until the actual launch at Spaceport, we'll be refining our control algorithms based off what we learned at our test flights. If anyone has any questions, I'd be happy to answer them. Oh. Yes.
Okay, can you hear me?
Yeah, I can hear you.
I don't ever sit in the back. Okay, so
In terms of arming the payload, you said you want to do that on the pad, but with integration, right, obviously there's some jostling of stuff. Is that something you considered about arming at the tent, or are we even allowed to do that?
Payload doesn't have any energetics, so the payload will be on when when we slide the payload and the PSB into the body tube, it'll be on, and then when we insert the remove before flight tag, once it's in the body tube, it'll turn off. But there's no energetics or anything, so I don't see it being on for that brief time. I don't imagine would be a problem.
Okay, because I know driving out there, it gets jostled around too.
It'll be off for that because it's within the body tube, so we'll have the pin in.
And then, just because I don't know anything about E. coli, how is the temperature going to affect it? Because I know certain bacteria and stuff have certain thresholds where after it reaches a certain temperature, it just dies off.
For those online, the question was, what is the effective temperature on E. coli? One of the reasons we picked E. coli rather than yeast is because E. coli is very friendly to high temperatures, whereas if we picked some sort of yeast strain, there's a fair chance it would just die from the heat. E. coli won't have that problem.
Yeah, for an exact number, E. coli can survive up to 160 degrees Fahrenheit, just from a quick Google search. I know we looked at it before as well, though.
So I know you mentioned controls for the experiment, and you, at least to my understanding, that was just a E. coli strain that had no aeration and just sat there. Is that correct?
Yes, that's correct.
And so I guess my question is, since you can read like the G-force data, wouldn't it be beneficial to aerate a strand to the equivalency of what it would be like if it wasn't stabilized on the rocket?
Yeah, so we do have our control on the ground, and then we have our sample that's in that capsule, the stabilization capsule, and then we have a third one that is somewhere else in the payload that is not protected at all.
Okay, thank you.
Sorry. How are we getting the E. coli there? Is it just going to be in a cooler?
Pretty much, yeah. I'm not even sure if it has to be in a cooler, but that is something we're still working on, but based off our preliminary research, we don't anticipate that being a problem.
Okay, so start simple. Why did you choose to put the electronics at the top and their other experiment on the bottom?
Electrical is, all that tends to be heavier, and we wanted our center of mass to be as far forward as possible.
Yeah, and that's mostly for the purpose of the air brakes and just for stability as well.
Yeah, I know you had a reason, but you want to remember to tell people.
That's true.
We didn't just flip a coin and decide what went where, right? Show them how smart you are. So in the 3D printing of the sphere, first of all, I would show a drawing of what it is, because it's a giant black ball. So when I look at the slide, it's a black circle. And that's, you talk about you 3D printed it in one piece, which is very confusing when I know you need to insert things and do it. Like, well, if you printed a ball, how would you put E. coli in a ball? That doesn't, right? So it's not really one piece because you've got an insert that's got a cap and all of that.
That's true.
So I would show, I think the best I saw on a later slide, 35 or something, you sort of had the drawing that. Show me that or some equivalent CAD drawing or something first.
Okay.
To tell me what you 3D printed, because it's just hard to visually see a black sphere and what's there. The one thing I'd explain is what I think those are screws up top holding the white part in.
Yes.
Like what they're going into, because I literally can't tell.
Yeah, we have.
It's black on black.
Yeah, we have threaded inserts that we're buying we can press fit into the plastic.
Yeah, so that's the part I think you need to explain that early before you show it, because it was just a little confusing. You have your cool little vibrational damper system, right? So where's the vibrational analysis that shows me that it actually damps vibration, since that's its purpose?
That is something we are still working on. That came together in the last couple weeks, so we haven't quite had a chance to do that analysis yet.
Then your cool video system, right? You got your fancy markers. What happens if those fall off or wear off?
That's part of what test launches are for, is to make sure that's not going to happen. But from our testing so far, they have not shown any indication of coming off, even when we run the sphere around and around and around and around.
So that's what I would mention. We've already sputtered a bunch
Mhm.
and didn't see significant wear because otherwise we won't know that you've already done that.
Mhm.
Right? So you've done testing and forgotten to tell us that you've already done testing.
Mhm.
Presumably you now saw your typo on sub
Yes.
35. So your control system, has that been tested yet? Like, oh, we have it to reorient at all. When is that going to happen? Because the first test you mentioned was your dart test.
Mhm.
Well, if you're testing your cameras, that means you have to know your control system already does what it's supposed to. So is that already tested, or do you just need to add a bullet point to your test list?
We've tested the computer vision and the control and the mechanical control separately right now, and then before spring break, we're hoping to conduct an integrated test of the two of them.
Okay, so I think a lot of that is, right, it's work you've already done. You just have to remember to tell us.
Yeah.
Because you forget. We don't know that you've done it, and we will not assume that you've done it if you don't tell us.
Yeah.
Okay, there are no questions in the chat, and we're nearing up on the 5-minute limit, so thank you for your questions.
All right, next I'll turn it over to Peter with avionics.
All right, I promise my slides are much shorter this time than at the PDR. All right, so I'm Peter Hall. I'm the avionics lead. I'll be telling you about our electrical and software systems. So the purpose of our sub-team is to design and again, primarily SRAD, as is the theme of the entire rocket, flight-critical electrical and software systems within the rocket to manage primarily recovery, but then the tracking and then control of the air brakes. So this is basically anything that's electrical that is not part of the payload is part of avionics. We also work to expose our sub-team members to skills and industry experiences that are not taught in class. I know the EC major specifically doesn't teach a lot of what I consider to be very relevant skills for just doing your job, so we try to expose that to our members as well. So going into our system requirements, so the most important thing we do is to eject the nose cone and deploy the drogue parachute at apogee. So we're tracking the rocket's motion, and when we are at apogee, so the highest point in our flight, we send a signal to recovery, which deploys or ejects the nose cone and thus deploys the drogue parachute. After that, we need to ensure that the main parachute is released at 1,500 feet, and that number can change based on the needs of recovery or the other sub-teams. We're also tracking the rocket's position using GPS at all times, and then we transmit back to the ground station so that after the rocket lands, we know where to go to find it quickly and easily. We're tracking a bunch of other different sensor readings as well, but those are not required. We just choose to do those for our own purposes. And then new this year is controlling the actuation of the air brakes, specifically to hit about 1% of within 1% of 30,000 feet. That's sort of just a threshold we came up with. We thought it to be a reasonable goal or something to strive for the first year of the air brakes. And then also we record flight video, just mostly for records keeping purposes. So our design overview, so again, we focus on a maximally SRAD design wherever possible and as to the extent allowed by the rules. We have a comparatively long conceptual design phase, so pretty much the entire first semester, followed by a somewhat accelerated assembly and testing phase. As we're doing so many different new items this year, we have a couple internal subdivision, and these people we refer to them as responsible engineers. They're responsible for a specific part of the system. So we have Dylan Williams leading the mechanical development. We have myself, Pranav Mula with the power electronics, Dersu Gorski with the flight software, Toby Simpson for the air brakes control, and Lauren Clark for the ground control software. And these people, as well as everyone else in the sub-team, are super essential to our success. I could not do it without them. So to go over the system overview quickly. So on the right side here, we have basically the majority of our SRAD electronics. So in the center, we have our SRAD flight computer. This is an STM32-based system. We have a variety of sensors and data storage methods, as well as an arming circuit and the eMatch switching circuit. This is supplied by one battery, so the battery powers the flight computer, as well as the SRAD GPS tracker and the camera. So all of these are connected electrically. An important thing to note is the SRAD flight computer is actually two separate circuit boards, so the air brakes significantly alter the pressure above where the avionics bay is mounted. So if we're measuring air pressure there, it will give us an inaccurate reading and will lead us to an incorrect estimation of our altitude. So we have the smaller sensor board Up above the payload, as Corey mentioned, we have a special second avionics bay up there, so that's what that is. We have our arming switch, so this is the removable flight tag, and this switch, of course, as is its purpose, it prevents the E-matches from being fired unless it is activated. We also have some COTS electronics, so that's commercial off the shelf, specifically the Altispectrum Easy Mini. This is our redundant commercial flight computer, and this is armed directly with a separate arming switch from the SRED system. We also have a redundant COTS GPS tracker, that's the Altispectrum TeleGPS, and that has its own dedicated battery as well. So a quick system overview. On the left there, you can see a CAD model of the avionics bay, and then we have a diagram next to it showing what's kind of going on. At the bottom, we have our battery pack. Above that, there's a power circuit board. We have our radio circuit board, which is actually what you see right here. We have the SRED flight computer, and then we have the interface or I/O board, which allows the circuit to interface with other parts of the rocket. And then again, of course, we have that second smaller system for measuring air pressure. On the right, you can see a partial integration. So you see the bottom bulkhead there as well as the mounting rods for circuit boards, and that again is the radio board integrated in the system. So starting off with the center of our SRAD electronics is the SRAD flight computer. So this is our primary flight computer, and it's built around an STM32 microcontroller. So that's a single core ARM architecture microcontroller. Does a couple important things. Of course, first of all is recovery events. So that's deploying the nose cone at apogee and then releasing the main parachute at 1,500 feet. Air brakes control, general data acquisition, and the GPS tracking via our radio board. So this flight computer specifically uses pressure, air pressure, and acceleration from which we can derive position and velocity. We combine those two readings to determine our current state, so our current altitude, using a Kalman filter. And this also is armed via a physical removal for flight tag. So that is a pin which is inserted into the rocket. When that pin is in the rocket, it is totally disconnected. The charges cannot fire. When you remove that pin, that closes the circuit and allows the charges to fire. And we have a sufficient debouncing circuit, an electrical circuit to make sure that's ultra reliable, and that small, I guess if the switch were to bounce or vibrate during flight, this would mitigate that. So the COTS flight computer, so we are required by ESRA, the Experimental Sounding Rocketry Association, to have at least one commercial off-the-shelf flight computer in the rocket. We chose the Altispectrum Easy Mini to meet this requirement. For one thing, it's very affordable. After the crash last year, we had to replace all of our COTS electronics, which was fairly costly. This one was much more affordable than an option like the Telemetrum. Also, it is a lot smaller, so as we have a larger payload this year and we're adding the air brakes, space is an ever-increasing concern. And additionally, it's widely used and well documented. Altispectrum is like a very well-known brand within the community. They have good documentation to describe their system, and we are familiar with using their hardware in the past. This device detects apogee barometrically, so this is also mounted far above the air brakes, where its pressure will not be affected by those. This is armed physically, like the ESRA flight computer, with a removable for flight tag. The same concept, except they're totally electrically isolated, so we have two copies, one for the SRED, one for the COTS. They are physically separated, they are electrically isolated, they are totally independent and redundant. To power all of our systems, we have a new SRED power system. So this basically allows us to take in a high voltage from a large battery and regulate that and filter that to be used by our SRED electronics throughout the system. Specifically, we have buck converters, which are voltage, basically it steps down the voltage from roughly 15 volts to 3.3 volts, which is our main digital logic voltage, and 5 volts, which is used for some things like the camera in a highly efficient way. We have about 80 to 90% conversion efficiency with those. Specifically, the battery we're using, so Ezra put in place some new battery regulations this year. So we have a 4-cell lithium-ion battery, and those are using 2,700 cells. So that's basically a cylindrical battery cell that is 20 millimeters in diameter and 20 millimeters in diameter and 70 millimeters long, and they're in series. So this board also, we implemented battery charging over USB-C, so we have a dedicated battery circuit. Actually, you can see it up here at the top. So this way we'll bring an extra battery charger just in case, but we don't need it. You can just plug in the bay to a charger as you would for your computer, and it will charge the batteries while it's integrated. We also simulated all of the power regulation circuitry in Spice. Spice is a circuit simulation software where you can put in various electrical components and set different voltages and currents, see how it will behave before actually building the circuit physically, just so we can be more confident in our system. So one of the new things we're doing this year is the SRAD radio. So in the past, we've used the Altispectrum TeleGPS for our radio tracking. This year, we have built our own around the S2LP RF transceiver. So that basically is a digital to analog converter, which we send in digital data and it gives us out an analog RF signal, specifically one in the 70 centimeter band at 433 megahertz. As far as we know, we would be the first team to implement a system like this, which is obviously a competitive edge, but also it gives us a little bit more flexibility in our own design and makes things easier for us in integration. This actually is a joint project between avionics and my capstone team. The capstone members are myself, Declan Caban, Pietro Levezzo, Christian Robinson, and Osman Casey. So far, we've had a fair amount of success with testing this board. We've booted it successfully. We can communicate between the board and the computer, and now we're just debugging some errors in our RF system to actually communicate between the two boards, but we expect that to be working soon. And again, we're using this as a redundant tracker with the COTS version just because it's the first year. We want to keep a commercial option in there just in case. So for both our SRAD and COTS tracking systems, we're looking into the antennas this year at a little bit more of a technical level. In the past, we've just kind of used whatever antenna and hoped it would work without really any analysis at all. So we are looking into actually validating our antennas for both the systems. And possibly, this is something we're actively doing like right now, developing our own antennas that will give us higher gain and better directivity. For all of our antennas, we are going to do some testing at the Electroscience Laboratory in their anechoic chamber, where we'll put in the integrated motor tube, coupler, and antennas to see what their actual radiation pattern is and how our large metal objects affect their gain and if it causes like undesirable reflections, that sort of thing. We're just really excited about this. We think it will give us a lot more certainty that our system will actually work. In the past, we've been on the pad and we are like just on the edge of losing connection with the rocket, which would obviously prevent us from launching the rocket. So we consider this to be like a pretty important endeavor. So the flight software is what is basically the code that is running on the SRAD flight computer in the rocket. So we have the ground control software, which I'll get to in a minute, but this is what's running in the rocket. And this is written, it's a fairly low-level embedded type of software. It's written in C, which is a common programming language for this sort of thing. And we're using a library or a framework called FreeRTOS, so Free Real-Time Operating System, to handle multitasking, as I'll get into in a little bit. We're also developing this in the Cube STM32 Cube IDE software. So this is a software provided by the same company that manufactures the microcontroller to allow for easier development. And this year we're we're looking at two different things when designing the software. One of them is that we obviously want it to be optimized for what we're doing now, but we're keeping the door open for a lot of flexibility in the future to change it as our needs evolve. So the flight computer, the flight software, in parallel with the flight computer, is responsible for a lot of different tasks. Specifically, it is collecting sensor data. So we have a lot of sensors. Importantly, though, we have our pressure sensor and the accelerometer, and we use that sensor data to time our recovery events. So we're looking at different data. Each data is going to have a different source of error and a different tolerance. So we're combining them and doing some math to ensure we can estimate that correctly. So we use that data to time our recovery events, but also to run the air brakes control algorithm and then transmit the data to ground. Also, the flight software is just tracking various systems within the rocket. For example, it's monitoring the power on the power board, so it's looking at making sure voltages are at the correct level throughout flight, that sort of thing. And again, it needs to kind of do this all at once, or at least all very quickly, which is challenging because it's only a single core processor. So we have this free RTOS library that allows you to run tasks in parallel. They're not actually in parallel, but it happens. They transfer between tasks quickly enough that we can have parallel-esque operation. I'll briefly touch on the controls. The specific math of the controls is a little bit too involved to discuss at length in this presentation. So if you're interested in that, you can talk to myself or Toby Simpson afterwards. But so far, we've basically described the system dynamics. We have a couple different equations. These two here can be solved to predict your apogee. As you can see, this is a nonlinear system as we have the gravity there. So it sort of has an equilibrium point at the ground. But these are sort of the basis of what we're using for our model. And we have a couple different methods of how to solve it. Or just general methods of solving differential equations analytically. We have not chosen one yet as we're still testing, or we will be testing the software and seeing how quickly it can run on the flight computer and the rocket. But this is the basis of our model. An example here of some of the analysis we have done. So I have a phased portrait of basically our state trajectories of the rocket. So what this is showing you here is essentially if you have any set of initial conditions at which you're beginning your analysis, which would be a pair of a current velocity and an altitude, as well as a drag coefficient, the different sort of levels of the lines are the drag coefficients. We can see how the rocket's flight will evolve if we don't supply any control inputs. So this just helps visualize our understanding of the system, and we can see basically during the flight, we are at this altitude and moving at this velocity. If we don't do anything, we'll hit this altitude. And if that's too high, then we can decide to make an adjustment to correct that. So the controls algorithm, we're actually reworking a lot of it right now. So we don't have a super clear picture at the moment. But essentially at the essence of it, it is a linear quadratic regulator. In very broad terms, how that works is you have a cost function, which you are repeatedly minimizing to get close to your specific goal. In our case, our goal is obviously hitting 30,000 feet. And we've linearized this into a couple different regions. The different methods of linearization are being explored. For us, the cost function is the deviation in altitude from 30,000 feet, which obviously we want to be 0. For the state estimation, so we do not want to rely on a single sensor for our prediction ability, as different sensors are more susceptible to different types of noise. So we are looking at an inertial measurement unit or an accelerometer and a barometric pressure sensor combined to predict our current states. And another important thing, I know a lot of people have asked about this, is our flight stage restrictions. So neither the air brakes nor the energetics, which are the recovery charges, will ever be deployed or fired while the rocket is traveling above a specific Mach. So I just have XX in there. This is totally variable. So as our aerodynamics and structural needs change, we can just basically set that to whatever threshold we deem appropriate. Right now it's about 0.8, but that could change. So the final piece of our system is the ground control software. So this is running on a computer on the ground, and this interfaces with the rocket via our radios. Basically, the rocket is transmitting telemetry data to the ground control software, which is reading it in and then displaying that for us to read and interpret. One new feature this year is the digitized version of our checklist. So we have an integration checklist, and a lot of the items on there can actually be checked electronically by the flight computer on the rocket. So this way, while the rocket's sitting on the pad, we can look at, for example, the voltages in our different power rails, or do we have continuity through our E-matches? Is the radio connected? Well, if the radio is connected, we wouldn't have telemetry, but it allows us to have a better view of what's going on within the rocket, even when we're not physically next to it. And we developed this primarily in the Python language using the DeerPy GUI library, which just gives us a lot more customization compared to other commercial options that we've used in the past. Here is a diagram of the ground control software. So we have, it's the view you see, so you can pretty easily reconfigure what windows are being shown at any given time. Right now we have a couple of different plots here for acceleration, ground speed, gyroscope, altitude, as well as a 3D model of the rocket, which will show orientation, and then a sort of a 3D trajectory map of the rocket state. We're also outputting a bunch of different data here from the sensors, as well as arming states of the E-matches. So basically what we're transitioning into now is, Ram? Oh no. the live stream back on, or?
Looks like so.
Okay. So, hardware in the loop testing is just a fancy word for testing our software on the hardware we are using. So we have our flight software. We can test a lot of it just on our computers we're developing it on, but we want to test it on the actual hardware it will run on in flight. So we were just trying to replicate the flight conditions as closely as possible. So we can, for example, simulate sensor inputs with serial ports, and this would just allow us to understand that the software not only works from like a logical perspective, but also that it works on the architecture it needs to run on during flight. And this just allows us to have higher confidence in our systems, as there is a good amount of risk involved with them, as I'll get into. So the risk to the project success. The first risk, and by far the most significant risk, is that the SRAD flight computer deploys the parachutes early. So for example, when we're going supersonic, if it tried to eject the nose cone, that would probably destroy the rocket. So the big thing to mitigate this is our software functionality locking by flight stage. So again, we're reading in sensor data, and we're looking at our velocity. If our velocity is too fast, and that can be anything above a configurable threshold, they'll totally lock out that portion of software. Those cannot deploy. And so just a lot of testing and very careful system design is how we're mitigating this. After that is that the SRAD flight computer does not deploy the parachutes when it's supposed to. So we mitigate this, first of all, through redundancy. That's why we have 2 flight computers. But again, just extensive testing and careful design, as is the theme with sort of all of these. Similar to the first risk, if the air brakes deploy early at any point in the flight before we want them to, that could be catastrophic to the rocket. So again, they are subject to the same locking requirements as the recovery charges, as well as, again, extensive testing. And I'll note for the risk 1 and risk 3, we are definitely being conservative on these. So we would rather not deploy the SRAD flight, not fire the SRAD flight computer at all, rather than fire it early, because we do have the redundancy if it doesn't fire at all. But if it fires early, the redundancy doesn't help us. The rocket may just be destroyed. And then finally, GPS tracking connection is lost. So this is a much less significant risk, but this will just make it more difficult to find the rocket once it lands. So for this, we're testing our antennas and we're testing our radios, making sure we can stay connected over a good distance, and it's behaving as we expect. So on the risk matrix, so the SRAD flight computer deploying early, so that is a severe risk. However, we think it is very rare due to our software locking, extensive testing, and also just being very conservative with that deployment algorithm. The SRAD flight computer deploying early, so similarly, we think that's pretty rare, not quite as rare, but, does not deploy at all. So this is slightly less rare, except it is a lower risk as we do have the redundancy of the COS flight computer. Air brakes deploying early as well, so that is a rare risk as it's mitigated through the same measures as risk 1, and it's slightly less severe. That's just because we're not entirely sure how that system behaves yet. GPS tracking being lost, definitely the most likely risk, just by nature of the nature of wireless networks is that they're fairly unpredictable or difficult to work with. However, if that happens, we don't expect any physical damage to the rocket. It just might mean more time walking around in the desert trying to find it. Okay, so the plan for the year. So we have started off with education and training. So the first part of the year was entirely focused on that, and this has slowly tapered off, though it continues throughout the entire year. We started off with basically research and conceptual design in the first month, so we've transitioned then into assembly. Now we're wrapping up assembly this week basically, and then getting into testing. So we're just testing continually until the test launch, and then depending on the results of that, we may continue afterwards in documentation and more testing. All right, are there any questions? Yeah.
So I'll start with a simple one. You have the 2 different computer systems.
Yes.
For redundancy, I get that. So would they disagree? How does your software resolve that issue?
So they are actually not, so as specified by Ezra, they just cannot talk to each other. So that is, unfortunately, we can't really, if I were building my own rocket, I'd have some sort of voting scheme between multiple flight computers. But for us, they are just totally isolated. So if one goes off early, it just goes off early. That's just an unfortunate part of how the rules are written.
Okay, so this is not really a question, but maybe a suggestion. Since you're talking about the avionics and the control system, somewhere I would first have talked through your expected trajectory.
Mm-hmm.
What's the time, the velocity, and the altitude of burnout we're sort of expecting? Because if you're aiming at 30,000,
Yeah.
because it just gives you context for
Mm-hmm.
what you're talking about. If you say, well, we're setting some Mach number, like, well, how fast were you going
Yeah.
before that? And how much has it already slowed itself before we're going to deploy? Things like that.
Mm-hmm.
To,
Yeah.
Note on that, in the beginning of the slides, me and Ron were first just beginning, I used to talk about an overview of the rocket. We went over a quick rocket overview that had our expected apogee of like 34,000 feet, and like our maximum velocity and acceleration, but it could be a compliment as well.
Yeah, I think.
Yeah, the max, but
Yeah.
telling me like the burnout and when we would, right, it's the next flight stage where you coast. Now I'm waiting to see you slow down versus, so for your particular system, that knowledge is
Mhm.
context, and it's good to have it right now, because I will have forgotten anything you told me at the beginning of the slide deck at this stage.
And we've also sort of we've tried to design our system to be as reconfigurable as possible because we've been doing it like in parallel with propulsion and aerodynamics, so we didn't always like have those answers at the beginning of the design process. But yeah, that's a good suggestion.
All right, looks like there aren't any questions in the chat. If there are any questions in the audience, we can go.
All right, well, time for Calvin to talk about recovery.
Greetings all, my name is Calvin Beal. I'm the Spaceport Recovery Lead this year. So our purpose is to safely recover the Spaceport rocket. That just includes deploying the nose cone at apogee, handling all the mechanical systems that the avionics has to manage. That means reducing shocks, trying to recover safely recover it, minimize wind drift. We want to basically design and build a single separation dual deployment recovery system. So essentially, we're only decoupling the rocket in one point for simplicity of structural reasons. So it's an interesting challenge for us. It provides a unique sort of system rather than just a basic dual deployment system. So we need pyrotechnic line release, parachute bag, all that kind of stuff. There we go. Yeah, okay. So we have a list of requirements that are based on the Ezra requirements. So since our rocket will be achieving an apogee of 30,000 feet, it must utilize a dual deployment recovery, meaning we basically have to have two sequences of recovery. Since the release mechanism is intended to be SRAD, it must be redundant, it must be ground tested and controlled from separate flight computers, as mentioned by Pather. The initial deployment must occur at or near apogee. We're going to do it at apogee. It's just the simplest, lowest velocity, lowest stress. There's no reason not to for us. The descent rate under the drogue, we're looking at 80 to 90 feet per second. That's just right in the middle between the upper margin and lower margin provided by Ezra. The main parachute must not initiate deployment above 1,500 feet. That's an Ezra requirement. I want to have the main parachute deployed, fully deployed and inflated by 500 feet just to reduce the velocity for impact. And all the recovery equipment must be protected from flame, from the recovery energetics. So we basically use a lot of Kevlar. We plan to use flame cloths, etc. And of course, it should be lightweight and volume efficient. It's a rocket. So here's the system overview. We have our drogue deployment systems. I'm going to use this little laser pointer. So we have our drogue parachute here. That's just the tiny little parachute that brings us down from 30,000 feet to 1,500 feet. Attached to that is the nose cone, and then on a extended line here, couldn't draw the whole thing, obviously it's long. Then we go down to the deployment bag. So we have our main canopy in there with all of its shroud lines and such. We have our bulkhead section, which basically retains everything. It's what everything's bolted to, as Corey mentioned. So then when we deploy our main, it kind of looks like this. So we have our drogue out here carrying the nose cone, and it's still retained to the rocket body because it doesn't have its own separate GPS. So we have to retain it to the parachute like this. And then the main rocket body and our included bulkhead section is suspended from the main canopy there. So as far as our drogue intercoupling system is concerned, we have our ejection pyrotechnics. We calculated a 4-gram main load and 5-gram backup load. That's with quadruple FG black powder. That just defines the size of the granules. It's about the smallest, most fine powder you can get. The canister design is recycled from last year. It's optimized for ideal combustion. We want to verify this when we go into our testing phases with our ejection tests. We'll get into that in a moment. We just have basic canopy care and packing, so we basically want to protect all of the non-flame-proof items from the recovery energetic flames, so like flame cloths. We're keeping the drogue north of the main canopy in its Kevlar bag, so that should provide additional protection, and all lines south of the bag should be Kevlar. And also just protecting things with sleeves where it might interact with body tube sections. We want to use double bow lines on all our knots. It's just highly secure. It self-tightens as you apply force to it. We use these shear pins to retain the nose cone to the rocket body until we want to eject it. So we need to make sure that we're able to shear those pins and also deploy the nose cone a specific distance. We'll get into that with testing. And the lines we use are all 800-pound polyparaffin terephthalamide, which is what Kevlar is, but it's nice to know what Kevlar is without just using the commercial term. And then the connection points, basically the main drogue line just attaches to the top side of that bag with a high-strength swivel and threaded connecting link. And then on all of the parts, like I said, it's just knotted in. So for the main canopy and deployment system there, this is basically the soft components of that. We have the deployment bag. It's got a conical geometry that basically is for the ease of deployment of the main parachute. It basically kind of convinces the parachute to come out a little easier, and it also fits into the nose cone system better because most of our system just fits in the north end of the rocket. So we use grommets and thimbles, and those are just to reduce friction in anywhere that lines might interact with sheets or other fabrics. It also reduces wear significantly. So for the canopy care, I'll show this in the next slide. I have a lot of visual aids here, but we got a highly densely packed parachute. So, I mean, this parachute bag itself probably weighs like 10 pounds, but it's only the size of a little, sausage. But yeah, so we want to Z-fold it so that just facilitates the parachute unraveling easier. We have flame protection, so it's in a Kevlar bag. Everything south here you can see is all Kevlar. So Kevlar has a really high temperature resistance, flame resistance, and it's very resistant to energy and impacts and such, as you know. For our connecting lines, our main shot cord is approximately 15 feet of 3,000-pound Kevlar line. That's got to be extra strong just because it's got to withstand the snap load of the main parachute opening. Our release line is a 5-foot, 800-pound Kevlar line. It doesn't need to be that strong. It shouldn't be withstanding loads over a couple hundred pounds, but it's also only an 1/8 inch in diameter. So going any smaller than that, you're looking at like sewing threads, which is absurd. But it does need to be Kevlar because it doesn't need to be flame resistant. So the sleeve is a 2-foot approximate sleeve. It's Kevlar weave. It's sewn in separate channels to prevent tangling and to have ease of line sliding. So the main shot cord needs to be free of this sleeve, and the release line end that slides needs to be free of the sleeve, but the middle line is permanently attached, which creates those separate channels. And so here's some visual aids. Here we have frangible links, or a frangible retaining, not a frangible link, my apologies. We have a frangible, basically retaining strap. It's essentially tape. It just holds these lines together. It basically keeps them retained until you apply a specific tension to them, which allows them to unravel, but it also keeps them very easily retained in the bag so that they don't come out prematurely. We have our folding techniques. Basically, we fold it up and we put it into the Z folding pattern, which, as you can imagine, as you pull the parachute out of the bag, it wants to fully unravel and be very nice. And then the parachute is permanently retained to the deployment bag so that we can fall as one part as by Azure requirements. And you can also see the release line thimbled attachment here, which basically goes through the flaps of the bag, as you can see here. So for the bulkhead systems, this includes our pyrotechnic line release mechanism, aka the PLRM. It basically functions off of an interference fit between those two pins. As you can see here, these two pins, as you can see, have an interference fit with this latch, So basically, the strain of those pins is not to be greater than what the interference fit can allow. So the function is essentially this latch cams along this pin. So if either one of these pins is fired, it can deploy the main parachute release line. It's anticipated we'll experience about 500 psi of internal pressure to exert the 25-pound pull force to overcome the friction of the pins just being under that force in that mechanism. The construction is just mostly aluminum. The latch is made out of a stronger aluminum because it's a smaller area and it's got to withstand the same loads. And then we use a lot of stainless steel for our hardware. It has lower tensile strengths and such than most other steels, shockingly enough. But when you account for the fact that the whole assembly is aluminum and it's threaded into aluminum, you don't really need it to be any stronger than that aluminum strength, and it is still technically stronger. We wanted to have a much more organized layout this year. We've had kind of a rat's nest in previous years. I should have put a picture in that, but it's a kind of messy sort of setup. So we have these recovery plugs, as you can see, on the sides of the PLRM. We have our ejection canisters on the side here. We have our U-bolt, and then we have our threaded rods, as you can see, attaching the bulkhead to the rest of the rocket. So for the expected forces, we expect an approximate 60-pound force from the drogue on average, just because that's the approximate weight of the rocket and the drag equation, all that lovely stuff. Approximate, maybe 130-pound jerks. Again, we could expect more than this. And we want to test for this. We just want to make sure nothing will break if we do experience a high jerk or if our apogee velocity is too high. There is a maximum approximate force of 1,000 pounds from the main parachute opening, and that's just based on the speed of our drogue descent versus the size of the main parachute canopy. This is subject to change if we change the diameter of our parachute. Say we want to land slower or faster, so it can increase or decrease. It can also change a lot based on ambient conditions and such. So we need an approximate 10 pounds per square inch to eject the nose cone and shear the 4 shear pins at 21 pounds each. Basically, if you apply 10 psi across that 6-inch diameter bulkhead, you get a couple hundred pounds of force. And that's more than adequate to take the nose cone and launch it about 9 feet or so. So here's more visual aids of the PLRM system that we've developed. These are basically some super basic SolidWorks simulations, just analyzing where that latch mechanism might fail. The factors of safety are extremely high. I think it's about 10x or so, depending on what load you apply. And so here's the full aluminum assembly with all the hardware included. We have a very neat little polished shoulder bolt there that is exactly 1/8 inch. So we have those keying marks in the base block and this pin that provide alignment so that nothing's out of, angle tolerance. So, and we also have countersunk bolts to keep everything aligned. So it ends up moving very nicely. We also use this dry lubricant. It decreases friction, makes everything run nicely. Here's a earlier drawing of the bulkhead. It's constantly changing as we realize we need to perform different functions. And then, we have the expected black powder load. And this is one we experimented with. It was a 0.025 grams, so 25 milligram or so, quadruple FG black powder, main and backup charge, because it's the same pin being pulled in 2 different points under different loads. The pull force factors of safety. So testing and validation. This is one of the major emphases I've made this year is on testing. In the past, I have witnessed none, as a matter of fact. So I can't tell you about previous year's tests. There weren't any, which is embarrassing, but this year we want to change that. So for our test regime, we have our semi-static tests. So this includes the pyrotechnics ground tests, as you can see in that first image. Our ejection tests, we want to aim to do those manually initiated, so just with like a 9-volt battery, and then avionics initiated, where we change the actual pressure in the body tube and let avionics deploy the nose cone based on their data. However Peter wants to do that. We have our dynamics tests. So this includes the automotive ground tests. Again, COTS initiated and SRAD initiated. So essentially we have either a frangible chain link that we buy off the shelf to deploy the main parachute, or we use the SRAD parachute release mechanism, which I previously elaborated upon. We also have our drop tests. The likelihood of these are entirely dependent on how available the skydivers are and how the weather is looking. And then we have our test launches for those. For general safety, we just want safe standoff distances with any kind of energetics, proper PPE or protective personal equipment, however that goes, and then just careful handling of the kind of pyrotechnics and stuff like that. So starting off, we have our SRAD pyro ground tests. So these are based on the expanding gas work principle. It's energy too, but you know. This basically validates our black powder calculations for the PLRM, mechanical principles for it as well, its ability to withstand loads, and it validates our SOLIDWORKS static simulations. So the rundown is essentially we have a weight that equals our expected load suspended from the component. We fire the charge and the mass drops to the ground. It's fairly simple, straightforward, and still fun. Here's some images of our latest test. This is the finalized PLRM assembly. And this is basically a sequence of the firing. It was, I would say, nominal. We had some wear on this latch mechanism, but I believe that was because I tried to sand it by hand and so it was an uneven surface. So that basically had a much more localized surface profile on that latch, which resulted in excess wear. So for the ejection tests, we have not yet performed these. We want to very much. The black powder charges are basically based on this set of equations. You can find these online. They're readily available. And this basically validates these calculations for the nose cone decoupling, the bulkhead's ability to withstand the loads from the ejections, our drogue deployment and packing techniques, and the fire resistance of all the recovery equipment. So these are all very important things. The drogue is kind of the leading charge of all of our recovery, and if that doesn't work, nothing works. So it's very important that we do these. The ejection tests, basically, the ejection charges are loaded, all recovery equipment is installed, we fire the charges, the nose cone is decoupled and ejected a distance, and we analyze the results. So for the automotive tests, these are a very interesting one we've done lately. This basically validates our ability for the deployment bag to free the main parachute. This is very important. This is something we've struggled with in the past. Basically, we would get weird tangling issues or things we couldn't have foreseen without doing these kinds of tests. So basically, this tests for that, the ability for the lines to function properly. So that's the shock cord, the release lines, the sleeves, and the general main deployment sequence. So everything that kind of happens when we're deploying the main. And also, again, the ability for the system to withstand some of the dynamic loads. We can't really test the forces from the main parachute. That would rip off my roof rack. I wouldn't want that. That would be unfortunate. And we've found that our time for deployment of the main parachute is approximately 1.64 seconds based on our footage. So here's a sequence of photos. I would have added a video, but PowerPoint videos are always problematic. So basically, here's a sequence of the main parachute deploying. Here you see the fully retained bag. Here's an instant that the charge is fired and the bag is still closed. The bag opening, slowly opening. See how the flaps are fully deployed there, and the bag is fully ripped off the parachute here, and here's the parachute deployed, breaking that frangible restraint that we had on top of the vehicle. Here's a test of the test equipment, because you got to test your test equipment if you're making it yourself. Basically, under the expected loads that we have, suspended using gravity as our friend. Oh, and that's a 30 kilo weight. It's about a 65-pound pull force that we tested on there. So for our drop tests, we also haven't performed these. We had an attempted drop test, but it was scrubbed. This would basically validate our ability for the deployment bag to free the main parachute, and the ability for all the lines to function properly. And the main difference between this and the automotive tests is that the main parachute would actually stay attached to the system, so it would actually test the strength of our bulkhead and shock cords more realistically than anything else. So essentially, a simulated ballast with all the rundown is, simulated ballast, all the recovery equipment, except the pyrotechnics, because the FAA does not want you to bring your own pyrotechnics onto planes or into airports. And it's basically dropped from an aircraft with a professional skydiver from 4,000 feet above ground level. We've talked to pilots, we've talked to skydivers. They say they're okay with it. They've done this kind of thing before with like pumpkins. So they're all right with it. And so to get around that FAA pyrotechnics issue, because it does need to initiate its own main parachute deployment, is we have the Cypress line cutter. It's FAA approved, completely commercial off the shelf. It was provided to us from a skydiver. It's basically what skydivers use to deploy their emergency parachutes if they pass out while skydiving. So And then for our test launch, this basically validates our fully integrated system in conjunction with the avionics and realistic flight conditions. And essentially, the rocket flies to 5,000 feet AGL. The drogue is deployed at apogee, meaning it's deployed 1,500 feet, and hopefully the rocket is recovered. Here's just some example footage from our last test launch last year. So risks to project success, they're big ones. So if the drogue parachute does not deploy at the correct time or at all, that's highly critical. That basically results in a complete mechanical destruction of the rocket. And we want to mitigate this with properly packing everything, ensuring everything comes off, doing our ejection tests, drop tests, all that good stuff. For our main parachute, if that doesn't deploy or at the right time, that's also critical. That usually results in significant damages to the whole system. So we want to mitigate that with, again, properly packing, lots of tests, you can see here. And then if a part fails mechanically, that's usually pretty critical. And again, just properly packing things, wrapping things in protective sleeves, or lubricating things, using proper tolerances, smooth interfaces, factors of safety, all those wonderful engineering things we all are comfortable with. So for our risk matrix, probably the most significant thing would, if there is no drogue deployment, essentially our rocket would crater into the ground. It would probably, I don't know, reach the ground at about Mach 1 or something. That would be, either way, it's fast and it's bad. So the biggest tests for this are the ejection tests and proper packing. It's a fairly simple thing. It's fairly rare, but it is the probably most severe thing that could happen. If there is no main parachute deployment, that's also fairly severe, although less so because we'll still have a slightly recoverable rocket. And again, we want to test this with the most rigorous test regimes, so cart tests, power tests, all those things, lubricating, cleaning, like the Navy. If there's a late or premature main deployment, that's pretty significant, although not nearly as much as the previous two. It basically means either the rocket will take way too long to recover because it'll land miles away, or it'll hit the ground a little too fast because the parachute couldn't decelerate the system in time. If a shock cord breaks, that is very significant. It's unlikely. It could be due to anything. It could be if it is attacked by body tube section, we want to protect it with sleeves. If there's excess force, it would just snap. So we want to do everything in our power to prevent that, because that would result in a pancake rocket. If the parachute release cord snaps, again, that's just an early parachute deployment. There's nothing too significant that would happen there other than we'd just have to walk further. And then if parts are burnt or damaged, that's also not nearly as significant because we've come down on burnt parachutes before. They get just a little scorched. Obviously, it's not ideal. We'd like to avoid it. So we want to use our Kevlar, our ejection tests, PLRM tests. We want to use our flame cloths and the Nomex materials, stuff like that. So for our schedule, most of the first semester was the initial designing and simulation of the system. Basically, we were prototyping and kind of making things out of recycled materials, stuff we found laying around, because we didn't want to spend a bunch of money on making prototypes out of expensive materials like Kevlar and grommets and thimbles and things of that nature. So later on, we did a lot of machining and sewing of the main actual components. So a lot of sewing machines, a lot of time in the student machine shop. Last semester, we didn't do a ton of testing. We were doing mostly fabrication and simulation. And this semester, we've done a lot more. This has kind of been the main focus of this semester, and we plan to do it throughout the rest of the year, even after the test launches. And then iterating on the design, we're kind of always doing that, but mostly in the end of last semester, start of this semester was the greatest period of iteration. We're always finding the little flaws, the little tiny things you need to fix. There's always something. And then the test launch, we want to basically make sure our system is prepared and checked to be able to go up, because everybody relies on us to come back down. And then cleaning up and finalizing, that's basically just going from less prototypes to more final products that we can present to judges that look nice. And then obviously researching and testing new ideas for future projects. We'd like to save more time in the development phase so that we can get all our equipment done faster, so we can do more testing in the nice fall semester weather. So we want to do a lot of that researching maybe later this year after we've finished our system assemblies. Any questions? press it.
So I'll start with simple things.
Okie dokie.
You mentioned 1,500 feet is the limit of where you can deploy.
Mhm.
You wanted 500 is the other end.
Mhm.
You didn't say where you actually did want to deploy. In between there, but do you have a specific number as recovery person that if avionics can make it happen, this is when I want it to happen?
Well, avionics, I guess I could have worded that a little better. Avionics, I want them to initiate deployment at 1,500 feet. And before 500 feet, I want that full main canopy deployed and inflating. I don't want it trying to inflate at 200 feet. I don't want it trying to get all wormy and squiddy. There's this weird phenomenon with aerodynamic stuff with parachutes. It's somewhat understood. Ask NASA guy.
So does that math work out? You said it takes 1.64 seconds to deploy.
Yeah.
How long does it take to fall from 1,500 feet?
About 9 seconds. So it's about a 10x factor of safety, depending, 9x factor of safety. If I can get the main parachute to deploy in 1.5 seconds, that gives me, actually, no, it's about 20 seconds. I'm wrong. Apologies. Basically, based on last year's test launch footage, we used the same size drogue and a rocket is of similar mass, and you basically just timed so it was actually perfect because you could time, because our main parachute didn't deploy then, so you could time the time between the initiation where you saw the puff of smoke and it hitting the ground with the camera, and it's about 20 seconds that we have before we hit the ground at our approximate 90 foot per second descent rate.
In going along with that, what is our landing velocity that we designed the parachute for?
For the test launch, we're going to be using a 9-foot parachute that was donated to us. It saves money. Our main canopy was lost, unfortunately, last year due to the structural failure. So the test launch, it's approximately 25 feet per second with that 9-foot canopy. And then for the actual competition, I want to aim for 20 feet per second, so that would be about a 12-foot canopy with a parabolic geometry, which is CD of 1.2.
And how much is your expected drift with this design? 'Cause obviously, you said you're trying to maintain it. You can't minimize because you don't control wind, but what are we looking at?
That is a very good question. Early on in the year, I did a very basic MATLAB sim. Essentially, under a mile. Again, like you said, it's highly dependent on wind, so I don't really have a particular margin other than as little as possible. So.
If there aren't any other questions, there's also no questions in the chat.
Lovely. All right. Pass it on to our propulsion lead, Abby.
All right, hi everyone. My name is Advaith. I'm the propulsion lead for this year. A kind of brief overview of what our sub-team does is throughout the entire year, we want to design a solid rocket motor system that is able to propel the rocket to 30,000 feet. And kind of our day-to-day idea of what we want our students to do is give students hands-on experience with propulsion test systems, and motor manufacturing. So we spend most of the year doing simulation work and testing work in the second semester. We have a lot of requirements for the propulsion team. Most of them are from Ezra, and they're hard requirements that we have to follow, but we also have specific requirements for our team that is kind of based on previous years of propulsion. Some of the requirements that are given to us from Ezra are designing and manufacturing an SRAD solid rocket motor system that propels it to 30,000 feet, in between 30 and 34,000 feet accurately and efficiently. We also need to have our motor simulation files successfully designed to match the project expectations, which I'm going to talk about below. And we also need to document all of our design and testing decisions with the goal of exceeding the expectations of the Spaceport America Cup. Some of our specific requirements that we're working on currently is keeping the apogee between 30,000 and 34,000 feet without air brakes. So this is just a lot of simulation work, kind of validating the motor system and making sure it's all good when we plug it into our other softwares. On top of that, we have to keep the rail velocity above 100 feet per second, which is also an Ezra requirement that is given to us and something that we are accurately working on, especially since we're kind of still in the mix of doing all our simulations. On top of that, more of a specific requirement for the propulsion team is keeping the pressure between 500 and 1,000 psi. This is based on just previous years of what has worked with us and what has given us our ideal thrust values. And on top of that, our main goal is keeping the motor system a lightweight configuration, especially because of the air brakes and all the other heavier components. We try to keep the motor system as lightweight but also efficient as possible. So kind of a brief overview of the system that we use. This year we are using 5 propellant grains, which is a decrease from last year. Last year it was, if I recall correctly, it was 6 propellant grains. Our grains this year are anywhere from 10 or 11 inches. We have 3 that are 11 inches, and then the last 2 are 10 inch long. On top of the 5 propellant grains, we have our nozzle, which kind of just accelerates the flow, our nozzle carrier, and our boat tail, as well as forward closures and O-rings and snap rings for sealing purposes. As you can see, we also have a liner, a motor liner that goes inside. Kind of a more specific description of all the motor hardware is we have obviously our motor casing that encapsulates all the grains and the other propulsion system components like the forward closure. This is a 4-inch outside diameter, which is the same as last year, and it's 53 inches long, which is a decrease from last year. The reason for this was we just wanted to keep it lightweight, like I said earlier, and we didn't need it to be above 53 inches. With this 53-inch long motor casing, there may be extra room, especially if we only design the propellant stack to be like 50 inches long. If we do have those extra inches, we'd have to use an aluminum spacer, which we have done in previous years and we have experience working with. Aside from that, we have our forward closure, which is used for sealing purposes. That's at the forward end of the casing, and it attaches the propulsion system to the rest of the rocket. And we also have O-rings and retaining rings that are used for sealing purposes and made of rubber and steel, respectively. Aside from that, we have our nozzle, which I talked about earlier, that it's a graphite structure that accelerates the flow of propellants to increase the thrust of the motor. And the dimensions of this vary year to year, and they're based on the calculations that we use on our software called BurnSim, which is where we model all the grain dimensions and etc. We also have our solid propellant grains, which is where all the fuel for the motor is stored in. It acts as a combustion chamber, and we are using ammonium perchlorate composite propellant, APCP, which we have been using for the past years of spaceport propulsion. On top of that, on the aft side, we have the boat tail and the nozzle carrier. The boat tail reduces drag on the rocket, and the nozzle carrier simply holds the nozzle. When they're kind of combined, they look like the bottom picture. So this year, for the first time, we are doing our first hydrostatic test. The purpose of this is to verify the structural stability of the motor casing up to 900 psi, which is around 1.3 times the maximum pressure that has been determined from our BurnSim calculations. The maximum pressure on those calculations is around 698 psi, so this gives us a safety factor of 1.3. The reason we are doing a hydrostatic test, like I said earlier, is to verify the structural stability. We haven't done it in years before, and our motor has been fine, but we figured it's obviously good to have extra safety when we know when we test our motor and launch it in New Mexico. Kind of a general way you hydrostatic test is just filling the motor casing with water and then pressurizing it. That's basically it. You just fill it, you kind of make sure it's sealed, and you just pressurize the top, like I said, to 900 psi, and we get our data transmitted from the pressure transducer. We have lots of safety protocols for this, which I'll talk about in a later slide, and it's very similar to the static fire test. The picture here is the hydrostatic test stand that we are using. This is from the Liquids project team. So we are borrowing it from them and kind of getting our own adapters to make it work for ourselves. As you can see, it's a little difficult to see, but this right here is kind of where our motor will go. Obviously, we'd have to lower this because our motor is 53 inches long. We'd just close off the bottom, we'd fill it with water from the top, and we'd pressurize it from the top using like this pressure hose right here. And kind of the reason we're using 900 PSI is because some of the equipment that the liquids test stand has is only rated to 900 PSI. The original plan was to do 1,000, but it's kind of easier if we use their equipment, so we're going 900. But that's a safety factor of 1.3, which is kind of matching our standards. With the hydrostatic test, since it's our first year doing it, we'd have to do a lot of analysis. The main analysis we did for this is calculating the maximum hoop stress in the motor casing, making sure that it doesn't break to overpressurization. Like I said earlier, the maximum pressure from Burnson was 698 PSI, and because of all the ratings on the equipment that we're using, the pressure estimations were done for 900 PSI. Like I said earlier, this is a safety factor of 1.3. After doing these calculations, we found the maximum hoop stress to be 94.6 megapascals. The material we are using is aluminum 6061 T6, which has a yield strength of 241 MPa, which means that obviously our maximum hoop stress is less than that, and that falls within that margin. This itself is a safety factor of 2.5. So that safety factor plus the 1.3 safety factor from earlier makes sure that this is safe and we're good to go for our hydrostatic test. As you can see on the right, we have a little MATLAB graph that kind of just shows the hoop stress versus radial location for our 900 PSI test. And yeah, all of our calculations showed that it was good to go. On top of that, we have done a MATLAB script for the thread analysis, basically just looking at the threads on the closure. One of the main things that we have been working on in the past week or so is designing a closure that goes to on the bottom of the motor casing. Because usually the aft side of the motor casing has the boat tail, which is obviously open for all the flames to come out of, but for the hydrostatic testing, we need to make sure it's closed. So we had to design something on SolidWorks that makes sure it's closed, and we calculated the max pressure that the aft closure can hold based on the inputs of threads. This MATLAB script is not finalized yet, but we are still in the process of doing it. Our goal is to have the hydrostatic test completed sometime around mid-March, and then after that we'll go into static fire testing, which I'm going to talk about now. So the whole purpose of static fire testing is to verify or design propellant stack, kind of see if, like our simulations, we have similar pressure, thrust, and burn time values based on the sims. Like I said, keeping the pressure between 500 and 1,000 PSI and having enough thrust where we are able to get to 30,000 feet in our competition. This year, like I said, we have 5 grains for a total of 53 inches. Although it may be less than that. This hasn't been finalized yet, and we'll probably be static firing sometime in late March, so we'll have it finalized by then. And also obviously testing for nominal burn, which will enable the rocket to reach 30,000 feet. We get our data from a DAC box. We get pressure and thrust data from the pressure transducer and load cell respectively. And numerous static fire tests may be performed if the motor does not meet competition needs. We have done this in the past. We have done several static fire tests, but it's not always required. It's just based on the results we get off of it. So these are the testing procedures for the static fire test, but the hydrostatic test procedures are pretty similar to this. Obviously, we want to verify the pressure transducer functionality and make sure it's actually picking up data before we go out to the field. We need to calibrate the load cell to make sure it's giving us the thrust data that we want from the static fire test. And kind of like on the more safety side of things, obviously assigning team members with different tasks. Usually we have a safety engineer who's in charge of everything, and we designate like 1 or 2 people to go out to the field who put the igniter in, so on, stuff like that. And then obviously safety training, especially for hydrostatic testing. This is pretty important when you're working with high pressures and obviously like water going to high pressures. So I had most of my members complete, it's called Base 11 training, and we're obviously going to make sure that's done before the hydrostatic test. And obviously for the static fire test, it's useful too. Some of the small requirements we follow is just keeping minimum 50 feet distance from the test. make sure it's safe for everyone. So as for the simulation stuff, this is what we spend most of our first semester on, and we're obviously still working on it right now. Total impulse of 27,300 Newton seconds, which is basically pretty similar to last year. The goal of this year was to keep it similar to last year because last year the motor system did not have any problems. So that is the total impulse. The average thrust is around 4781 newtons. The burn time is 5.56 seconds, and the max pressure is around 700 psi. This is, like I said, just pretty similar to last year. It's only changes are obviously we have less propellant. It's a 53-inch propellant stack. And here's a nice little graph of the burn time versus thrust and pressure. Usually with these type of graphs, you want it to be like pretty steady. Obviously, you want your thrust and pressure. It's usually going to be a straight line, but this is good enough. It kind of conforms to all our needs of the propulsion sub-team. So, yeah. Some of our flight simulations, we talked about this in previous slides. We went over it in the first few. Sarah was talking about it. But propulsion does have a pretty big factor with determining all of these. Aside from burn sim for the motor simulation, we also work on Open Rocket, which is the rocket simulation file. And our predicted apogee is 34K feet. Our max velocity is around Mach 2. Max acceleration is 17.78 Gs, and our mass with motors is 81.695 pounds. We're still finalizing this. There's a lot to be done before the competition. Like I said, one of the main requirements we're trying to follow is keeping the rail velocity above 100 feet per second, and kind of playing around with this and seeing if we could change any weight, especially with the propulsion propulsion system, can obviously help us with our requirements. So also one of the first things that we are doing this year is optimizing our coefficient of drag. It's a lot different this year because we're using air brakes for the first time, and the drag values are just pretty wrong. Like, I wouldn't say they're wrong, but they're different on Open Rocket. So we're trying to get the exact values from the aerodynamic sub-team from Sawyer and putting them into Open Rocket so that it kind of helps out our apogee. Doing a preliminary analysis leads it to a reduced apogee of a few thousand feet, going down from like 36K to 34K. Obviously, this is because there's more drag. When you increase the coefficient of drag, the apogee will go lower. We're still working on this currently. This is a plugin that we've just found we were using online from Open Rocket. And as the aerodynamic sub-team finalizes the drag coefficient values, we'll continue our work on this. But it's kind of good just to have a more accurate simulation file, especially with accurate drag values. So this is also something we're currently working on. As for risks to project success, the main risks for propulsion are the same year to year. Obviously, a motor CATO, which is a catastrophic event. We do static fire tests to ensure propellant stability every year, make sure that the propellant we choose, amount of grains, is all stable and good to go. Structural failure, if it gets overpressurized, past its capacity, and ends up exploding or leaking. That's why this year we're doing our first hydrostatic test to ensure the strength of the motor casing. As for a shuft or failed ignition, this is pretty rare, but by kind of doing a dress rehearsal before like testing or static fire testing, we can practice proper replacement and just make sure that's good to go. And also, our inability to reach target apogee, it's one of the things we're working on, obviously keeping it between the 30 and 34,000 range. That's why we do a lot of extensive simulation throughout the entire year with Burn Sim and with Open Rocket. As for our risk mitigation, obviously any type of explosion on the motor is pretty severe and we wouldn't want that to happen. So that's why we have it in the severe category, but it is pretty rare because we do so much testing. I mean, definitely like at least 1 or 2 static fire testing, and we're doing hydrostatic testing, we do all the simulation. It's pretty mitigated. As for a shuft or failed ignition, obviously practicing static fire testing procedures, proper placement, kind of doing dress rehearsals, which we are planning, and all of that. and obviously, like I said earlier, doing burn sim and open rocket simulations to help us out. So the plan for the year kind of changes based on what the needs of propulsion are. We spent most of the first few months researching improvements from last year, seeing if anything went wrong last year, and looking at all the files, motor simulation files from last year. We start doing our preliminary simulations, and then we start looking into static fire testing as the semester ends, and we're in the second semester. Obviously, calibrating the load cell and verifying pressure transducer functionality, which we're doing right now. This year was a little different because we set up the hydrostatic test. We've been working a lot, like I said, with the liquids team for that, using their resources, their test stand, and obviously we have to order our own adapters, which we are working on, calculating the hoop stress, designing the aft closure. That's what we're working on, but at the same time we do need to finalize our motor design because static fire testing is coming up soon. So we're finalizing the motor design and burn sim, kind of splitting up the work. So hopefully the goal is to have a static fire done and a hydrostatic test done in March so that as the semester ends, we can finalize the competition motor and be good to go for New Mexico. That's it for my presentation. Are there any questions? Lane.
What igniter are you using?
For the test fire, we'll probably just use an igniter that we get from one of our mentors. But for that competition, I'm not too sure.
Yeah, honestly, we'll talk more with Todd
Yeah.
about that once it gets a little closer. What we're doing and everything.
So you had your thrust curve slide.
Yeah.
You want to just talk through it towards burnout, the three plateaus there, what's going on?
Yeah, so the maximum burn time was around 5.6 seconds. So usually when it's done burning, it kind of just goes like very steady. You're right that it's kind of a little stagnant, like plateaus like that. I'm not too sure the reasoning for that, for why it just kind of goes flat, but usually, I mean, that's what it's supposed to look like, I guess.
And not too long after this, you mentioned you're going to have 18 Gs of acceleration potentially. So payload team is fine with 18 Gs?
Yep, that's what we're doing our simulations at.
So when is sort of your drop dead date for making changes, right? You're talking about getting aerodynamic data, new CD values, but at some point you have to tell them to quit giving you changes and design something and do it. So sort of where do you set your date for that, for them to stop changing things on you so you can finalize them?
Well, most of their data is already basically finalized. You guys are kind of going by like Mach number, right? So I think they're working on the supersonic Mach numbers right now, the data for that. But as they'll be done in the next few weeks. So the goal is to have everything done by the first static test fire, most of the simulation. But if that doesn't work out, we have until the competition to make any changes, which is in June.
Just to clarify on that too, we have kind of deadlines imposed on us by the competition, so we have to static fire by early April because of just their competitions. Right, we don't have any questions in the chat.
Cool. I'll pass it on to Sawyer on aerodynamics.
All right, hello everyone. My name is Sawyer Hammond and I'm our aerodynamics lead this year. So the aerodynamics sub-team purpose is that we want to gain insight into how the rocket performs through all phases of flight, and primarily what we look at is the drag. And then with our drag data, we want to also assist with developing accurate altitude predictions. And then also along the way through this whole process, we want to enhance our current members' understanding of fluid dynamics and CFD. So just some system requirements that we sort of set upon ourselves are that we want to analyze the drag and stability characteristics of the rocket's components. And then based off of these, we can recommend geometry changes to improve flight, and then acquire drag coefficients of the rocket through all flight regimes, and we can utilize these to accurately predict the rocket's apogee. So mostly what we've been working on this year is our air brake system drag analysis, our full flight drag analysis, and then working on our wind tunnel testing as well. So just sort of the overview of the air brake system. Once again, the idea is that 4 panels will extend from a housing in the body tube. These are large flat surfaces perpendicular to the flow of the rocket. That they should be able to create large amounts of drag, and that we can create enough drag at command to control our and reach our goal apogee. And so pretty much the setup for how we simulated these in ANSYS Fluent is we simulate the rocket at intervals of 25% of air brake deployment, utilizing a quarter body fluid domain. This is just sort of to cut down on computational cost because our rocket is symmetrical about 2 planes parallel to the rocket. So we can just simulate a quarter of our body rather than having 4 times the amount of cells for a full body simulation. Utilizing a K epsilon turbulence model just for a higher solver speed. Then the boundary conditions we utilize in these simulations are obtained from open rocket simulations, and we test the rocket at each 25% of air brake deployment at about every Mach 0.1. So an overview of our results from these simulations can be seen on this graph here. Pretty much the consensus is that full deployment of the air brakes will almost double the drag coefficient of the entire rocket. And so we will hand over these drag coefficient values over to our controls team. They will be utilized during flight to sort of predict and control our altitude. And then just looking at this plot here, while the drag coefficient does change with speed, while the air brake is stored, the drag coefficient is around 0.3, and while it's fully deployed, it's on average around 5.57. So something else we've been working on a lot this year is our full flight drag analysis. So this is just without any air brakes. We are obtaining drag coefficients of the entire rocket throughout the entire flight, set up the same as our subsonic or air brake simulations. And so we will use these drag coefficient values in our open rocket override to sort of improve the open rocket drag coefficient values, particularly in the transonic flight regime. And then here's just sort of our conditions at about our max dynamic pressure or our highest speed. We've got a drag coefficient of about 0.33, total drag force of a little bit under 1.5 kilonewtons. And then here in this pressure contour, we can sort of see where we've got our shock waves and expansion waves forming all over the rocket at this high supersonic speed. And then the pie chart sort of shows just at what percentage does each piece of the rocket contribute to this drag value. It's about what you would expect. For our testing and validation, something that we've been working a lot on for about the past month is our getting ready for our wind tunnel testing. We have fabricated a 1/5 scale model competition rocket from 3D printed parts, and we've brought them down to a pretty smooth finish. The plan now is to go over to Bowles Hall, utilize the wind tunnel there. We will record drag forces on our 1/5 scale model rockets, and after that, with our obtained wind tunnel data, we will run CFD simulations at identical conditions to the wind tunnel test, while maintaining our models utilized in our competition rocket analysis. And this way we can sort of validate the accuracy of what CFD models we are using right now. And then in addition, we, from our test launch, during the test launch, we will be utilizing our air brake control system, and then pretty much from the data gathered from our test launch, we'll be able to determine if our air brake drag coefficient values, maybe we over or underestimated them with our simulations. Risk to project success, errors from meshing quality. If our meshes are a poor quality, we won't be able to accurately represent our different flow characteristics, especially around in our boundary layers and areas where there's a lot of activity going on. Over underestimation of drag, this also sort of goes back to our mesh quality risk. If we overestimate our drag, especially produced by the air brakes, we may accidentally overshoot our goal apogee, and then the opposite for if we underestimate. Issues with scheduling wind tunnel access. A lot of capstone teams now at Ohio State University are going to be utilizing the same wind tunnel that we have planned to use, so we might struggle to find a time to fit in there. And then time shortage, just getting all our work done before the end of the semester. And then our risk mitigation, risk matrix, errors from meshing quality, impact would be somewhat minor, but likelihood is a little more likely, just due to our limitations as far as computer power goes. And what we've been working on to mitigate that is consistent Y+ values, trying to make sure that we are accurately capturing our boundary layers. And then also we conducted some mesh convergence studies earlier in the year, trying to accurately identify which cell sizes we can use without sacrificing much accuracy. Over and underestimation of drag, the likelihood of that is a little less likely than our meshing quality. It is still possible, and the impact of that would be somewhat significant. But we are working on mitigating that with our wind tunnel testing, some hand calculations, and our test launch data. So we've got a lot of experimental sort of testing to mitigate that, and then also our hand calculations. Issues with scheduling wind tunnel access. Likelihood is probably pretty possible, as there are a lot of teams trying to utilize the same wind tunnel right now. But if we plan our process ahead, we probably only need one section of an afternoon in there, and that's all we would need. And time shortage, looks a little bit cut off there, but we're pretty on schedule. We don't have a ton more work to do at the moment. We've worked efficiently as a team by delegating tasks, and yeah, so pretty good on that. Our schedule for the entire school year. Last semester, we spent a lot of time on teaching new members CFD, specifically the software ANSYS Fluent. We spent a lot of time on our post-motor burnout subsonic drag coefficient database, particularly with our air brake analysis. And then sort of going through the end of last semester and into this one, we've been working on our full flight drag coefficient database, spending a lot of time in our supersonic areas, and we're about finished with that. Constructing our wind tunnel model, we've spent about the last month working on that. We're pretty much all done with that. Wind tunnel testing, we just have to wait to get scheduled in there, and we should be able to finish it pretty quickly, hopefully just before our test launch. And then once we do our test launch, we'll get the data from that, and we can further validate our models. All right, that is all I have. Are there any questions? Yeah, in the back.
So, why did you decide not to have like a scale model of the air rates in the wind tunnel testing?
So we could have also done that, but I think it would have been unessential. If we could do that, but we're just doing our rocket, and if we can validate that our current models from CFD with just that, we could have done either really, but I mean this is just like ever so slightly simpler. But if we can validate it with just the rocket, then I mean our CFD models are sort of applicable to all of our like different geometries we would have tested. Yeah, Dr. Ritchie.
So several questions. One,
Okay.
how do you train your team to use Fluent?
So initially what we did was we had a couple 2D sort of tutorials. I think one was like a supersonic wedge, one was, might have been a flow across a cylinder. And then we moved on to sort of our quarter body 3D rocket simulations. I had laid out a pretty extensive Word document with pretty much all of our inputs and then reasons behind each one. And then they would go through that, and pretty much throughout a lot of last semester and still going through this one. We have our meetings, we go through those simulations, then if anyone has any questions or if there's any errors, then we'll troubleshoot those together.
Because as you know, I have to teach a whole bunch of people to make you all do it, not really teach it.
Yeah.
So if you have thoughts on ways to make that smoother,
Okay.
have you done it? Let me know. Because you've been on the other side of that. When is it you want to use the wind tunnel?
So
Late March?
pretty much as soon as possible now. I had emailed John about it, I think sometime last week when we finished our model. And then I think I'm going to talk to him about it tomorrow. So just really as soon as possible. Hopefully before late March, yeah.
Yeah, I was going to say, it's going to either be really soon or
Yeah.
probably after spring break.
Yeah.
Or during spring break. Pretty much guarantee almost no capstone team wants to be running during spring break. So yeah. You were talking about some computational limitations just from using the, I assume the Scott computers.
Mm-hmm.
Very easy to get you guys an OSC account if you want to remove computational limitations, right? I mean, that's
So-
virtually free.
We did actually get access to a previously started OSC project for BSLI, but I think there was some trouble with one, the version history of the ANSYS products they had, but then also there was some sort of like limitation on when you launch the Fluent solver itself. But so what we've done now is we just recently got some HPC licenses directly from ANSYS, and we asked the OSC to implement those, and so we can utilize those now, yeah.
And then just a related but not relevant to what you just presented in question. In the future, would you guys ever be interested in using the Mach 2 wind tunnel?
Definitely would prefer that over the Bulls Hall one, yes, yeah.
Because in theory, getting it plumbed back up would be available in the future. Not going to help you guys, it won't be ready, but.
And then also you asked earlier just about the transition piece design. So the general idea of it is just to reduce the base drag of the rocket, just because if we decrease the area earlier on, there's not as much of an area drop in the back, there's less base drag. And then pretty much, so that was just the initial why we chose a transition piece, but for the specific length and shape, we last year and the year before that did some studies pretty much on, we tested different lengths of the transition piece, and then sort of plotted out, like on a y-axis it would be, then obviously as we make it longer, it weighs more. So we plotted out average drag plus weight of the piece versus length, and it kind of leveled out, like we sort of minimized the drag and weight value. It leveled out at about like 20 inches long. We could have kept going longer and maybe gotten it like slightly better as far as drag goes, but then also that's a a harder piece to produce compared to what we've made in the past. So we just went with 20 inches.
Yeah, so it's just somewhere, since he was talking about it, like, if you're gonna reuse something, it would be good to talk about why we thought it was good in the first place.
Yeah.
So we've got a couple of questions from Joey Cayley online. I'll give them to you one by one. First one is, have you looked at how any turbulence from the air brakes impacts the airflow over the fins and the rocket stability as a result?
So we didn't specifically look at how the turbulence from the air brakes affect the fins, though we sort of, we haven't looked at that specifically. I guess we can do that. As far as stability of the entire rocket goes, we did do some analysis on that, just with sort of like our center of gravity versus center of pressure, ensuring that our center of pressure is below our center of gravity when they are deployed and when they're not deployed. And it seemed like we had a good amount of distance between the two.
Cool, all right. The second question out of 3 is, did you look at max Q with and without the air brakes extended?
Yes, but I think I did that like near the beginning of last semester, just sort of to get like a random ballpark max drag value on the air brakes. However, we won't be deploying the air brakes at any speed above around Mach 0.8, and that's also until after the motor's completely burnt out. So I did look at it sort of just for fun, but yeah.
And the final one is, what airspeed will you be testing in the wind tunnel?
I think the maximum value it can go to, I think the maximum safe value I was told, I don't remember exactly, but it's like.
It's listed maximum 65 meters per second.
Okay.
So you can plan for 60, and whether it fully runs to 65 or not, I don't know.
Yeah, so somewhere in that range of 60 meters per second. And then because of that also, I'm in contact with a couple professors just about whether or not we should try to trip a turbulent boundary layer somewhere on the rocket to try to get it to be more analogous to our CFD simulations also.
And that's everything from the chat.
All right.
All right, and that's everything we have for the CDR. If anyone has any follow-up questions that they didn't get answered previously, feel free to ask them now. Does anyone in the audience have any further questions for the leads? All right, anything in the chat room?
I'll ask one. Do they really make you do this ridiculously long of design reviews every time? Or do you self-inflict this?
It's actually self-inflicted, believe it or not. Just to keep it somewhat, I guess, kind of like a professional sphere sort of thing. It's a good excuse for us to compile all of our information and, I guess, kind of note-keep all of it. And also,
I just ask because some of these student competitions really have put the workload. Like DVL passes a 60-page report to run.
yeah, we do have a technical report at the end of the
You're
year.
like, where's the fun in writing a 60-page technical report? Sorry. So I was just curious how much of this was mandated versus what the team was choosing.
Yeah, so our design reviews are both self-inflicted, but we do have like progress reports and a final technical report, but not the most documentation, I guess, that we could have compared to other teams. All right, and I guess if there's no further questions, thank you everyone for coming out. We really appreciate it. We really appreciate hearing your questions and your feedback. And we'll see most of you at the next meeting, hopefully. All right, and thank you everyone online as well.